Welcome back to the course entitled Elementary Electrochemistry. In the previous lecture, we have discussed about how to determine the EMF of an unknown cell using a standard cell, and then we have discussed about the construction of Western cell. So, in this lecture, I am going to talk about the EMF of a cell and the free energy change. The chemical reaction taking place in a galvanic cell is always exothermic, that is, a quantity of heat is evolved. If E is the EMF of the cell, supplying Q quantity of electricity, then the electrical energy released is E into Q, that is EQ. Now, with each equivalent of reactants involved is associated with 1 Faraday, that is written as F of electricity, and if N equivalent of reaction takes place, then the electrical energy is equal to NFE, right? Helmholtz pointed out that in a reversible cell, the decrease in the free energy of the process is equal to the electrical energy obtained from a galvanic cell. So, that is minus of delta G is equal to NFE. So, now from our knowledge of basic thermodynamics, we know from Gibbs Helmholtz relation, delta G is equal to delta H plus T del delta G del T at constant pressure P. So, now we replace this delta G by NFE, that is minus NFE, which is equal to delta H plus T as it is del delta G del T P, or simply one can write E equal to minus delta H by NF plus T del E del T P as del T delta G is nothing but del minus N F E by del T, or minus N F del E del T. So, now that N F which was here, when it comes down, gets cancelled and you get this equation. The minus sign also gets removed. So, you get the expression like this. So, this equation also can be used to calculate the EMF of a cell, right. Further, we know that delta S is equal to minus of del delta G del T P, and then you can replace delta S equal to minus del G del T P. So, you can again replace delta G by minus N F. So, you can write del minus N F E by del T P, or equal delta S equal to N F del E del T at constant pressure P. So, here we are getting the entropy change of a cell from its EMF and temperature coefficient of EMF, right, because this is the temperature dependence of the EMF. So, if you know EMF and its temperature variation, then you can easily calculate delta S for a given cell. So, let us discuss one simple problem here. Consider the following cell. at 25 degrees centigrade. Pb solid used as electrode, PbCl2 in aqueous medium is with HCl some molarity, aqueous HCl, and AgCl solid as the electrode. So, of course, when some electrode the cell is written like that, the left side is negative and right side is positive, and it is given that EMF is 0.49 volt and dE dt is equal to minus 1.8 into 10 to the power minus 4 volts per Kelvin, right. So, it says calculate A, the entropy change when 1 gram mole of Ag is deposited, and B, the heat of formation of AgCl if the heat of formation of PbCl2 is minus 86 kilocalorie, right. So, how to solve this problem? First, we need to write down the cell reaction. Half lead plus AgCl equal to half PbCl2 plus Ag. One can also write Pb plus 2 AgCl giving you PbCl2 plus 2 Ag and so on. So, now we know delta G is equal to minus NFE. So, when you replace these values, what you get is minus 1 into 96500 divided by 4.2 into 0.49 calorie. Why? We are dividing this by 4.2 is 4.2 joule per calorie. So, we want the result in calorie. So, we converted it into calorie by dividing it with 4.2. So, the value turns out to be minus 11.26 calorie. And then when you try to calculate delta S, which is equal to NF dE dt, you can simply replace the values as 1 into 96500 coulomb into dE dt is given as minus 1.8 into 10 to the power minus 4, and again divided by 4.2, and the unit should be calorie per Kelvin, that is minus 4.14 calorie per Kelvin. So, what we have got? The entropy change, right. So, now we need delta H. which is nothing but from our thermodynamic knowledge of thermodynamics, delta G plus T delta S. So, now we have delta G is equal to I think this is not calorie, this is kilocalorie, because this is like this is kilocalorie. So, this delta G is minus 11260 calorie plus T is 298 into minus 4.14 calorie per Kelvin. You see this 298 is Kelvin. So, that per Kelvin and Kelvin gets cancelled. So, at the end you get minus 12494 calorie is your delta H. So, now the heat of reaction, that is the delta H that we have found, is the sum of the heat of formation of the reactants and products. So, one can write delta H reaction is equal to heat of formation of Ag plus half the heat of formation of PbCl2 minus half the formation of lead minus the heat of formation of AgCl. So, now at standard state, the heats of formations of pure elements is taken to be 0. So, it is nothing but half of H PbCl2 minus H of AgCl. So, H of AgCl is nothing but half of H PbCl2 minus delta H of reaction. So, now what was the heat of formation of lead chloride? It is given as 86 kilocalories. So, that is, this value is 86 kilocalorie, always the delta heat of formation is negative. So, we take it as minus half into 86,000 minus the delta H that we found in the previous page is 12494 calorie. So, the heat of formation of AgCl is nothing but 30.506 kilocalorie. So, this is how one can estimate the heat of formation of a reactant that is involved in a chemical reaction in an electrochemical or electrolytic cell. So, there will be several problems similar to this in your textbook. So, you should go back and try to solve similar problems using the method I have shown, and you may have to utilize some other similar related concepts of thermodynamics which is taught in a different course to solve such problems. So, we will continue from here in the next class. Thank you.